Section 11.3 Reactions in Aqueous Solutions. Here's our objectives. Describe the information found in a net ionic equation and predict the formation of a precipitate in a double replacement reaction. Alright, here's an example of an equation, and pretty common. AgNO3 plus NaCl gives you AgCl plus NaNO3. If we want to talk about a complete ionic equation, we're talking about an equation that shows all of the dissolved ionic compounds and dissociated ions and everything else. In other words, everything that you see that has AQ, that's going to dissolve in water. And when it dissolves in water, you're going to get the ions. So you're going to get Ag, which is a positive charge. And you're going to get nitrate, which is a negative charge. You're going to get sodium. You're going to get chloride. That wasn't very good. Let's try that again. You're going to get some chloride there. All right. And over here on this side, well, you see that this is a solid. That means that when those two things meet, they won't dissolve in water. So the silver from the silver nitrate and the chlorine from the sodium chloride, when they meet, they form a solid precipitate. And so you get this, and that's going to be that particular compound. And you can tell because of the solid and so on. And then we still have the Na plus and we have the NO3 minus. So here's my complete ionic equation. And all we've done is, divide these things up because that's what happens when they're dissolved in water. That's what they would be. But notice that on the left and on the right you have things like NO3, some Na plus, Na plus. Anytime that you have the exact same thing on both sides of the equation, those are known as spectator ions. And we can delete those. We can cross those out. So we can get rid of those because they really don't do anything. They're still floating around in the water just like they were before. They're not part of the main equation. So what we had right here, before I cross those out, that's the complete ionic equation. What we really want to get to is what we call the net ionic equation. And when I cancel out all those spectator ions, notice that I'm left with silver plus Cl minus yields AgCl. This is our main thing that's really taking place here. This is our net ionic equation. When we balance this, that we have to balance the elements. We also have to balance charges. But if you look at this silver, there's one silver on the left, there's one on the right, there's one chlorine on the left, one on the right. There's a positive and negative on the left, that equals 0, and obviously compounds are 0. So this is a balanced equation. This is my net ionic reaction here, or net ionic equation. So we talked about spectator ions, talked about those spectator ions like I said, and a net ionic equation shows just the things that are actually taking place in the chemical change itself. Got to balance the charges. That is important. We talked about it in the last one. The last one did it automatically. Some of them they don't. Take a look at this one. If we want to break this up, remember we're going to break up the things that say AQs. So we're going to have some lead, and we can't break that up. It's just one thing. We've got silver, which is a positive. We've got nitrate, which is a negative. We get this silver over here, which is a solid. We've got some lead, which is a 2 plus, because nitrate is 1 minus. There's 2 of those. And we've got some nitrates. And I don't have, erase that. I don't have to put in the 2. I'm going to balance it later, so I don't have to put it in here. And now, taking a look, are there any spectator ions? Anything that's the same on both sides? And you say, oh yeah, I can get rid of these. Those nitrates, they cancel, so they're done. So what I've got left is my Pb solid plus my silver ion. I've got my silver solid. Now those are different. Understand that this and this are different. And same thing with the lead. And I've got this. So if we look at this element-wise, it looks like it's balanced. but it is not balanced charge-wise. Notice that there is a +1 charge on this side, but there's a +2 charge on this side. Both the charges and the elements have to balance. So I would need a 2 here, which of course means I need a 2 there. Now, if you go back up, just to make sure that, you've got, oh, that doesn't seem to make a whole lot of sense. You know, if you go back up here and you balance this equation up above, take a look at it. Nitrates aren't balanced. There's one nitrate here, but there's 2 over here. So I would have to balance it like that. And if I do that, I would have to balance it like that. It'll come out the same as you had before. You know, if you had the whole equation, it'll come out the same as that. Okay. Alright, so the net ionic shows all of them. It's balanced in respect to both the mass, in other words, the elements, and the charge. Let's take a look at this one. We've got iron 3 chloride plus potassium hydroxide, and it forms, and notice that they always got to tell us something that doesn't dissolve in water. They've got to give us something. Remember we talked about it's going to be a precipitate, or it's going to be a molecule, or we're going to get gas, in double displacement reactions. So here's a precipitate. Now let's write this out, and I'm going to just separate these out right away. So we got iron 3, so it's Fe3+, and Cl-, and I'm not even going to put those compounds together. We could, and then we'd separate them, but there's not really much point. So it's K+, and hydroxide. And we know that this is going to be a solid. So this is going to be together FeOH parentheses 3. And then, what we'd get, this is double replacement, so the iron's going with the hydroxide, that's what we got, and potassium's going with chlorine, so it'd be KCl, well, K+ and Cl-, because those would stay dissolved in water. Okay, couldn't quite get my minus on there. So, if we look at spectator ions, we're going to see, well, chlorine, that one's there, potassium, that's a spectator ion. So I'm left with this, Fe3+ plus OH- yields FeOH3. Let's balance. I can either go trying to figure out how to balance the charges, or I can balance the elements. I always find the elements are simpler to start with, so let's balance OH's. And we've got 3 there. And now we've got a 3+, we got 3 negatives, so we got a 3-, so that equals 0. And net charges on compounds are 0. So there it's equal. So there's my balanced equation, my net ionic reaction. Alright, you try this one. So stop the video, see if you can do this one. Alright, so on this one, notice that what's formed that is no longer an ion is water. It's a molecule, and when those meet and they form molecules, that does make that reaction take place. So we can start with this and we can say, well, what's the same on both sides? Well, it looks like I've got some calcium on both sides, and I've got some phosphate on both sides. So really my net ionic reaction, or equation rather, is OH- plus H+ yields H2O. Charges are good. There's a negative and a positive, that's 0. And hydrogens and oxygens are good. Alright, so that's good. Now, if we want to predict whether a formation, something that we mix together is going to actually form a precipitate, there are some rules that we use to do that. One of the best things is this table on page 344. So you can look in there, or it's right here. And this kind of gives me some ideas of what's happening here. So here's what it says. It says if I have salts, by the way, salts is kind of a general term. It just means ionic compounds, basically, is what salts mean. Salts of alkali metals and ammonia. That means alkali metals. Those are like lithium, sodium, potassium. Anything made with lithium. So like lithium chloride. Or sodium. Anything made with sodium, like sodium hydroxide or whatever. Any of these compounds formed with alkali metals always tend to be soluble. In other words, those aren't going to be one of those precipitates that we're going to find. Same thing with nitrates and chlorates. So you see anything that is ending in an NO3. Okay? So if I've got something like NaNO3, nitrate, must be soluble. Chlorates, soluble. Even this one you'd know because the sodium is soluble. Okay? And then we come to the sulfate salts. Remember, sulfate is SO4. So things that have sulfate in them, things are soluble except for these. So, if we had something like calcium sulfate, which, calcium's there. Let's say we had, what would be a good one? Let's say we had lithium sulfate. Okay, that's going to be soluble, but all these other ones aren't. So things like silver sulfate, that would not be soluble, or barium sulfate or lead sulfate. So sulfates except for those. So if you see a compound that's lead sulfate, mercury sulfate, calcium sulfate, those would be insoluble, therefore that's a precipitate. That's what we're looking for. Alright, down here, same thing. Things that are chlorides, in other words, things that end in chlorine, that have the chlorine on them, are going to be soluble except for things with silver, lead, and mercury. We did one with silver, so, but things like AgCl, that's not soluble. So you're going to find that as a precipitate in things. And then the last, most carbonates, phosphates, chromates, sulfides, and hydroxides tend to be insoluble. So if you see a compound that contains a carbonate, probably insoluble. So what you do is when you look at this double replacement reaction, you try to figure out, is there something that's insoluble? And if there is, then that's going to be my solid. Excuse me. That's going to be the substance that's going to actually create this reaction, make this reaction go. So that's what you look for. All right. So if we look this up, we've got sodium, carbonate, barium, nitrate, and we're going to look in that chart and we're going to say, well, which of these things would make insoluble compound? So, our sodium, the plus, it could go with carbonate, it could go with nitrate. Well, we know that almost everything in sodium is soluble. So that's probably not a good choice. So chances are it's barium. So it's probably a barium compound. And then we could look, it's going to be barium and nitrate or barium and carbonate. Well, they also said that most nitrates are soluble. So now we're looking for, is it, if we have barium and carbonate, well, it says in the chart, carbonates, most of them are insoluble, so that's good. And barium tends to be insoluble in a lot of things. So it must be these two things put together. So the compound must be BaCO3, that is a solid, that we get that solid precipitate from. And then the other things are just going to be, like what's left is going to be sodium. So we would have some sodium ions and we'd have some nitrate ions. But they're just spectator ions. Once again, you could cancel those out. They're spectators, sodium. So this is my main one that we're trying to find. So that's what you need to do. You look in the chart, try to figure out which one is no longer soluble. There you have the end of Chapter 11.